Hello and welcome. In this lecture, we're going to continue our study of eigenvalues, eigenvectors. Specifically, we're going to study what are eigenvectors. Okay, so what are eigenvectors? We already saw eigenvalues for an operator and we saw eigenvalue exists for an operator. So, suppose lambda is an eigenvalue of an operator t, then the subspace null t minus lambda I. Okay, so we know when lambda is an eigenvalue of an operator, t minus lambda I has a non-trivial null space, right? T minus lambda I is singular, so t minus lambda I has a non-trivial null space. So that null space, null of t minus lambda I, is given a special name. It's called the eigenspace of the operator t with eigenvalue lambda. Okay, and a non-zero vector in this eigenspace is said to be an eigenvector. Okay, so this is just a basic simple definition. We defined lambda such that t minus lambda I has a non-trivial null space, and you go to the non-trivial null space, pick any vector, you call it an eigenvector. So why is this vector so interesting? So before that, let's see how to find eigenvectors. Just like we did eigenvalues before, looking at why they are so interesting, we figured out a way to compute eigenvalues. Likewise, how do you compute eigenvectors? It's actually quite easy. You just find the null space of t minus lambda I. We have done this so many times, right? So we know how, given a matrix, we know how to find the null space. So you just find the null space. That's all. Okay. So you go to the matrix M of t minus lambda I to x y is 0. You just solve this. One of these will be a dependent variable, the other will be an independent variable. You put that, and then you get the equation in a straightforward way. So here is the critical point. For every eigenvalue, once you know a particular eigenvalue, there has to be at least one non-zero vector, because the dimension of null t minus lambda I is at least 1, because it was singular, right. So there is at least one non-zero vector for every eigenvalue lambda. Okay, important point to remember, and you can just find it quite easily. Okay, so what is this intimate connection between eigenvalue and eigenvector, and why are they so interesting? So notice what happens here. This is a very equivalent definition for the eigenvalue. If there is a non-zero vector v such that Tv equals lambda v, then lambda is an eigenvalue of t with eigenvector v. Okay, so here is this is very easy to prove fact. It's very easy to see. This is equivalent to everything we've defined so far, and this is a good way to collectively think about the eigenvalue and eigenvector together. So what is going on here? There is this non-zero vector v, which is the eigenvector, and if it is the eigenvector, what does it do? This operator, when it acts on v, simply multiplies v by lambda. Okay, this lambda is a special value and this v is the special eigenvector such that when t operates on v, it simply scales it by lambda. Okay, you just get Tv equals lambda v. Okay, it won't happen for all lambda and it won't happen for all v. There is a special combination between lambda and v which makes this happen, and that's very nice and particular way to define eigenvectors. So this is a good way to think of eigenvectors. Okay, so notice here a very easy fact. If v is an eigenvector, any scaling of v, c times v, is also an eigenvector. Okay, because it also belongs to the null space of t minus lambda I, right. So another way to see this equivalence, I hope you see this, you can push this lambda v to this side and then take v sort of outside, and you'll get t minus lambda I times v equals 0, and v is non-zero, so t minus lambda I is singular, the null space has some vector. All of these tie together in this definition. Okay, so clearly, so when v is in the null space of t minus lambda I, so c times v will also be in the null space, but you can also see it in this equation. If you multiply both sides by c, I see that t times cv equals lambda times cv, so cv is also an eigenvector for this operator t. Okay, so here is another wonderful little property which sort of makes the eigenvector and eigenvalue very crucial for understanding operators. Turns out, if you really want to understand an operator, you want to know its eigenvalues and eigenvectors. Okay, why is that? That's because eigenvectors are intimately connected to what are known as invariant subspaces. Okay, supposing you have a linear operator t, if v is an eigenvector with a real eigenvalue, now this real eigenvalue is sort of crucial here, otherwise you may not get a very meaningful sort of subspace that you are interested in. Okay, so then t minus lambda I v equals 0 is tv is lambda v. So eigenvector is only scaled under t. So what does that mean? So when you only scale the eigenvector, so you have the R2 here, and here is this line. Okay, now this line under T, right now this if this line is the null space of T minus lambda I, okay. So, I have an eigenvector V here, okay, and this eigenvector V when scaled by C is also an eigenvector. So, when I scale it, I get this line, red line. So, this red line is part of my eigenspace, it's my eigenspace in some sense, right. So, every vector here is an eigenvector. So, what happens when T acts on a vector on this line? It only scales it, okay. Any vector on this line, when T acts on it, it only scales it, which means if you scale a line on this red line, you will remain on this red line, okay. So, this entire red line, when V becomes an eigenvector, this entire red line passing through V and the origin is preserved by T. It is invariant under T. This line goes to the same line under the action of T, okay. So, that gives you a good understanding of what your operator is, okay. So, you want to understand your operator, you really want to know what the operator cannot change, okay. So, the operator can never change this line, this eigenspace line, it will keep it the same, okay. Individual vectors within it, it may change by the multiplication by lambda, but overall the space itself is preserved by the operator, okay. So, this is a property that makes eigenvectors, eigenvalues so special, and you will see later on how we will exploit it when we look at powers of matrices amongst many other applications, okay. So, basically the point is the line through origin and V is an invariant subspace of R2 under T, and you need the real eigenvalue because this will stay in R2, otherwise it will go off to C2. In C2 you may have invariant subspaces, but we are more interested in R2 in some sense, okay. So, this invariant subspace property is a very crucial property for eigenvectors and eigenvalues, okay. So, here is a bunch of examples, okay. So, one can go through this. So, maybe I should pick up one or two quick examples just to show you how I will do the same example as before, how this worked out. So, we had lambda 0.5 and lambda 1.5, right. So, if you want to pick lambda equals 0.5, my m, maybe I call this a minus lambda I, you see is 0.5, 0.5, 0.5, 0.5. Notice how this is rank 1, okay. So, this guy is rank 2, when I did a minus lambda I got rank 1, okay, it became singular. Of course, I knew this would happen, that is how I found my lambda, right, I found my lambda to make this singular, so it became singular. So, you find the null space of a minus lambda I is just solving this equals xy, it is very easy to see, this is going to be so you can see to find null space you have to do this, maybe I will write it down for one particular case, it is quite easy to see this, times xy is 0, that is the same as x plus y equal to 0 or y equal to minus x. So, you can keep x as an independent variable, y as the dependent variable, and then you see that eigenvector is 1 comma minus 1, okay. So, that is an eigenvector. Any multiple of this is also an eigenvector, the anything that lies on x plus y equal to 0 is an eigenvector, okay. So, you can go back, and it is always good to check that everything worked out right. So, what should the eigenvector do? If you do a times the eigenvector, what should you get? A times the eigenvector, okay. When a multiplies the eigenvector, you should get some lambda times a, right. So, this better be 0.5 into this, okay. So, let us do the multiplication, you do here 1 minus 0.5, 0.5 minus 1, which is the same as 0.5 minus 0.5, which is the same as 0.5 into 1 minus 1. So, notice what has happened here, the multiplication by lambda, okay. So, everything has worked out properly, right. You fixed lambda so that this is going to become singular, and then you find a vector in that null space, and then when you plug it back into ax, av, you get lambda times v, okay. So, it is just an illustration to show you how these kind of things work, and you can repeat it for other things, but I will just warn you about a few interesting things here. If you look at this case you will get complex eigenvectors. So, your eigenvalues will be complex. So, your eigenvectors will also be complex. Okay. So, maybe we will do this example also. It is an illustrative and good example. 1 1 minus 1 1, right. So, how do you find eigenvalues? 1 minus lambda into 1 minus lambda equals minus 1. So, this is the same as if you solve it, you are going to get lambda to be equal to 1 plus I and 1 minus I. Okay. So, you check this out. This is a quadratic equation, you will get this solution. So, now how do you find eigenvectors? You want to look at so let us say lambda equals 1 plus I. Okay. How do you find eigenvectors for lambda equals 1 plus I? So, you are going to do minus I 1, right, minus I 1. Okay. So, these two times x y equals 0 0 you have to solve for. On the face of it, you may think that these two are not the same equation, maybe the rank is not 1. So, rank is not 2, right. So, rank is strictly less than 2, it's in fact it is going to be 1. How do you see it? You can multiply both this column by I, right. So, if you multiply this column by I, you get this guy, right. So, you have to think in complex numbers, sometimes the scaling you may not see. So, this first column scaled by I gives you the second column. If you multiply by I, minus I into I, minus I squared, that is 1. Minus 1 into I is minus I. So, this is actually a scaling, you may not see it immediately, it is a scaling. So, this is the same as minus I x. So, if you want to really see it, you can do the elimination. So, minus x minus I y equals 0. So, you do first equation. Second equation, how do you eliminate? You do 1 minus I times the second equation. Okay. When you multiply by I and subtract, you get 0 equals 0. So, the second equation is linearly completely dependent on the first equation, only the first equation matters, and if you solve it, you get y equals ix. You take this as a free variable, an eigenvector is 1 comma I, right. You can take any other value for x also, but 1 comma I is there. So, you can go back and multiply 1 1 minus 1 1, multiply by 1 I, you are going to get 1 plus I minus 1 plus I, which is the same as 1 plus I multiplied by 1 I. Okay, do you see that? 1 plus I multiplied by 1 is 1 plus I. 1 plus I multiplied by I is what? It is I minus 1, right? Do you see that? So, it is the exact same thing. So, this also works out. So, notice what happened, because you got complex eigenvalues, you also end up getting complex eigenvectors. Okay, so only then when you multiply, finally everything will work out properly. Okay, so this is how it will work when you have the complex case. Okay, the third problem also I want to illustrate, because that is an important and particular type of problem. So, notice what happens here, 1.501. Okay, so let us do that. So, when you do 1.501, something very interesting will happen. This is going to be 1 minus lambda square equal to 0. So, you are going to get lambda as 1 comma 1. So, there is only one eigenvalue itself, but it occurs twice. Okay. Algebraically in the equation it occurs twice, but you have to only do one for the finding the eigenvector. So, how do you find eigenvector? You have to subtract 1. So, you are going to go 0, 0.500 multiplied by xy equals 0, 0. So, the only thing you are going to see here is you need x can be anything, but then y has to be 0, right. I hope you see that this is the same as y equal to 0. So, any y is equal to 0, it is going to give you that. So, which means for instance an eigenvector, non-zero eigenvector. Okay, so my E dot is my, I do not want to keep writing eigen all the time. So, you keep getting x can be any value, y has to be 0, this will be an eigenvector. So, check that out, 10.51, 10 gives you 10 times 1, right. So, this is the everything checks out, but you notice here you have two eigenvalues of value 1 and you got only one eigenvector. Okay. So, here what will happen in these two examples, you have two different eigenvalues. Okay. So, you can repeat the same thing for lambda equals 1.5. So, if you repeat the same thing for lambda equals 1.5, what are you going to get? So, this a minus lambda is minus 0.5, 0.5, 0.5 minus 0.5, right. And then the eigenvector, as you can see, something in the null space is 1 comma 1. You can check this also. This 1 comma 1 will also be a proper eigenvector here. So, you have an eigenvector here which is 1 minus 1. You have another eigenvector here which is 1 1. Okay, 1 1. So, you got two eigenvectors, one corresponding to lambda equals 0.5 and one corresponding to lambda equals 1.5. Same way also you can do here. See, you got an eigenvector here for lambda equals 1 plus I. If you repeat the same thing for lambda equals 1 minus I, what is going to happen? You are going to get the matrix. I will do it really quickly here. So, if you do 1 minus I, you are going to get I1 minus 1I. Okay. So, here you get y equals minus Ix. So, the eigenvector is going to be y equals minus Ix 1 comma minus I. So, 1 comma I and 1 comma minus I are two eigenvectors corresponding to the two eigenvalues 1 plus I and 1 minus I. Now, interestingly, in this example, you get only one eigenvector. Okay, so maybe I'll write this as 1 comma 0. You get only one eigenvector. So, you got I mean, sort of got two eigenvalues, but they were the same, but you got one eigenvector. So, notice this difference. This difference is sort of crucial. It will come back and haunt us later. Don't think of it as some simple artifact. This is a very important and interesting thing. Okay. So, in contrast, let us look at another example which is given right here, a very simple example where it is 1 maybe instead of 1 0 I will take 2 0 0 2. If you take this, the eigenvalues end up being 2 comma 2. What about eigenvectors? If you do eigenvector, right, so this a minus lambda I, a minus 2I becomes just 0 0 0 0. Okay. So, now what are eigenvectors? You can take any two vectors, right. So, I can take for instance 1 0 to be an eigenvector and 0 1 also to be an eigenvector. So, anything I do, right. So, go back and think about why 1 0 and 0 1, any vector is an eigenvector, right, because the null space here, null space is R2. So, any non-zero vector is an eigenvector. Okay, do you agree with that? With the eigenvalue 2, you take 2 0 0 2, you multiply any xy, what will you get? 2x 2y, okay, which is the same as 2 times xy. Okay. So, any non-zero vector is an eigenvector. Okay. So, when you do that, when you have a null space which is very big like this in R2 itself, you basically take the basis of null space and stick to the linearly independent set of eigenvectors. Okay. These are the two linearly independent, these are two I mean this is one basis. So, these two are one set of linearly independent eigenvectors. So, it is enough usually to give one set of linearly independent eigenvectors. So, you just give 1 0 and 0 1 and you got two vectors. So, notice here also we had two eigenvalues which were identical, but I got two linearly independent eigenvectors. Contrast that with this situation. When you had 1 1.50, you are going to get only one linearly independent eigenvector, you are not going to get the second one. Okay. That is an important thing to remember. Okay. The last example in the problem set is this one. So, this has got 1 minus lambda 2 minus lambda equals 0. So, you have lambda equals 1 comma 2. Okay. So, here again notice how if you have any of the off diagonal elements being 0, the eigenvalues will end up being the values on the diagonal, right. So, that is reasonably easy to see because the right hand side will go to 0. So, the eigenvalues will become the eigenvalues on the diagonal. So, diagonal values will be the eigenvalues for diagonal matrices and all that. Now, what happens to eigenvector? So, you can quickly see this in your head. So, when lambda is 1, okay, for lambda is 1, the eigenvector is going to be 1 0, and for lambda is 2, the eigenvector is going to be 0 1. Okay. All right. So, anything on the x axis is an eigenvector here, anything on the y axis is an eigenvector here. This is different from the previous case. It is not like any vector is a eigenvector, anything in the x axis is an eigenvector, y axis is an eigenvector, there are no other eigenvectors outside of that. Okay. So, the eigenvalues work like this. So, hopefully these give you different interpretations of how the eigenvalues and eigenvectors will look. And what about invariant subspaces? Okay. So, anytime you had a real eigenvalue and a real eigenvector, you will have invariant subspaces. Okay. So, here in this case in 1 2, x axis and y axis are invariant. invariant is x-axis, y-axis, isn't it? This is the y-axis, this is the x-axis, no? So, if you go back and see here the entire R2 is invariant, okay, invariant is R2. If you go back here, for this one, the x-axis is invariant, right, that was the null space here. If you go to this guy, what about 1, 1, minus 1, 1? When you end up having complex eigenvalues and complex eigenvectors, there are no invariant subspaces of R2. Okay, there is nothing invariant here. And then if you look at this guy, here you will have invariant subspaces. So, for instance, x plus y equal to 0, this is invariant. This one is x minus y equal to 0. So, these two lines are invariant, right. So, these two lines, I am sorry, these two lines x equals y, x equals minus y, these two are invariant. Okay. So, I hope these operations are clear. This give you a good glimpse of what are all the various possibilities. The last one I am going to allow you to do it as an exercise. You will see here in this case, you will end up getting complex eigenvalues and complex eigenvectors, and this is a rotation by theta, right. When you rotate by theta, nothing is going to be invariant, okay. So, you can't get real stuff there, right. So, these are all nice intuitive ways to connect what the transform is doing to whether or not there can be invariant eigenspaces, whether or not there can be real eigenvalues, okay. So, I hope these points are clear, okay. So, basically these 2 points I want to emphasize. If you have a diagonal matrix, right, the diagonal elements are the eigenvalues, you can easily go through and find them, and you do not have to do any quadratic equation solving. If you have an upper or lower triangular matrix also, the diagonal elements are eigenvalues, okay. So, these are very easy in this case, otherwise it becomes, you have to solve a quadratic equation for finding the eigenvalue, okay. Thank you.